Lucene queryParser in Lucene. Now we are focusing on Lucene queryParser. queryParser API. This module provides a number of query parsers: flexible query parser, classic query parser, complex trace query parser, extendable query parser, surround query parser, span queries, query parser building query object from XML. If you are new to query parsers, a flexible query parser's standard query parser is probably a good place to start. Here you can see the control flow of query process. With linear scan, linear scan is a simple process of sequentially going through each line of the system and checking for the parameter, that is condition given in the query. This is precisely how Unix grep command works, and it also more fairly well with the wildcards and regular expressions. If the size of data set being search size is not too large and the hardware being used reasonably powerful, linear search is the simplest way. However, linear search start showing the performance degradations beyond a medium size document. The world around us is too experiencing an information explosion. In fact, the amount of data that needs to process to extract information has quadrupled over at least 10 years, thanks to the advent of connected world, handheld devices and IoT. Linear search cannot scale to meet those needs, so we need something more sophisticated and performant that can handle massive dataset while still providing relevant results at reasonable speed. Linear searches also limit what kind of queries can be answered. For example, there is no way to define query that seeks close matches of the given pattern. Suppose an instance that we search for document with the words flower and sunshine within proximity of 3 words in a document. Doing so with linear search is impossible. Also, there is no notion of ranked result. That is, given a query, a result is either a match or not for a linear scan. If we want some sort of ranking, we cannot use this linear scan. The inverted index is a data structure used to store data in an inverted manner, that the terms are mapped to a document in which the terms appear. Any unique term appearing in any document is made a part of the inverted index. To create an inverted index, the fields within the document are first split and tokenized. A shorted list of all unique terms are created, and the documents that contain corresponding terms are populated. While being fast for single term query, inverted indexes are also answer an important class of questions, similarity queries. This figure shows the typical way a query is processed in IR systems, information retrieval systems. A query comes in and is passed and is split into individual tokens. Token is an independent term having its own semantics in a query. For example, consider the following query: find all people who drove to college yesterday. In this scenario, tokenizing the query will lead to the independent terms such as drove, college, yesterday, and to. Stop list. Stop list consists of words that are used in the associated language to form the structure of sentences, but are not necessarily useful for semantics matching and searching. For example, in sentence Alex went to London, we see that the word to is a stop word because that helps form a structure of the query. However, it cannot necessarily contribute anything to semantic assessment of the potential document match, and so it should not be considered on the same lines. Stop words are filtered out before further processing to help limit the number of tokens in the index. to ones that can contribute to the relevant document. Of course, later on we might discover some of the semantically able words are not useful in matching a relevant document, but that is done stage by stage. Stemming. Queries can contain words in the different forms with different tenses, spelling, and associated grammatical semantics. For example, drive, drive-in, drives are all based on the same word but differ in their structure. However, for semantics matching, the actual structure of the word is of little value. What really matters is the root word, which will contribute to calculate the overall relevance of a document to the query. Another advantage of discounting different structure of the same word is to allow the one to match the remaining. For example, query containing the word drive should match document containing the word driving. This increases the recall of the query result. Recall is defined by a breadth of the return result, that is how many documents match a given query. Unlike the relational database, IR systems can answer queries with the semantic element with them. That is, any document can match the given query. The trick is to identify most relevant ones and eliminate the unnecessary noise. Recall is the width of a document and return result. However, too high a recall and return result will have lower correctness. Too low a recall and return results are very small in size. Most IR systems struggle with this trade-off. Stemming is the process of reducing words to their base word and removing structural differences between words that originate from the same root. However, stemming can be crude in the operations. For example, stemming can employ a crude heuristic to remove parts of the word which can sometimes lead to weird semantic outputs. While this is efficient and works most of the time, the more sophisticated way to deal with this requirement is the art of lemmatization, rewriting words using a given vocabulary and depending on morphological analysis of the tokens of the query. Lemmatization is beyond the scope of current discussion. To avoid linear search, you can index the set of document in advance and use special queries to get the right set of results. Consider, for example, set of document with the range of word present. Let's use a group of related books shown. Books database in action world of Lucene introduction to information retrieval. Let us assume that we have to serve queries across all three of these books. Doing so requires what we index data across all three books so that we can efficient in query operations. Note that there are multiple ways to do same thing. We can create a separate index per book or index all three books in the same index. Note that these books will have the same key terms in common. For example, except search to be present across all three of the text. Similarly, bytes is another term that can repeat across all three texts. The naive indexing technique is to maintain independent metadata about each of the document, effectively discarding the common terms present. This method is a waste of space and is inefficient for serving queries that seek matches across all text. To implement inverted indexes, you first need to understand concept of term and the term document incident. So a term document incident matrix. Here you can see queries connected to query tokens via pass query. Query tokens tokens are connected to stop list via filtering. Stop list is connected to stemming. Stemming is connected to index, and index is connected to retrieved. Index is connected to Boolean or similarity query via retrieve relevant document set, and Boolean or similarity query is connected to ranking docs via ranking. As an example, we can consider org.apache.lucene.queryParser.classic package. A simple query parser implemented with Java CC. As an example too, we can consider this code segment. Here the query parser, class query parser. This class is generated by Java CC. The most important method is query parser base dot parse string. The syntax for query strings is as follows. A query string is a series of clauses. A clause may be preceded by a plus or minus sign indicating that the clause is required or prohibited respectively, or a term followed by a semicolon followed by a colon indicating the field is to be searched. This enables one to construct queries which search multiple fields. A clause may be either a term indicating all the documents that contain this term, or a nested query enclosing in parentheses. Note that this may be used with plus or minus prefix to require any of a set of terms. Thus the BNF, the query grammar is query here equals clause asterisk, clause equals here plus and minus, then term dot and within brackets a term or query. This is in the package org.apache.lucene.queryparser.classic. Here in this construct, this create a query parser, and this is string f, the default field for query terms, and this is the analyzer used to find terms in the query text. In this parse method, this is the parses a query string and returning a query. The parameter is string query here, the query string to be passed. As an example 3, we can consider org.apache.lucene.queryparser.flexible.standard.config package, a standard Lucene query configuration. The package org.apache.lucene.queryparser.standard.config contains a Lucene query configuration handler, standard query config handler. This configuration handler reproduces almost everything that could be set on the old query parser. This is about standard query Lucene, standard Lucene query configuration. Now we are considering Lucene 9.7.0 query parser API. Apache Lucene, the Apache Lucene the query parsers. This module provides a number of query parsers: flexible query parser, classical query parser, complex trace query parser, extensible query parser, surround query parser, span queries, query parser building query object from XML. If you are new to query parsers, the flexible query parser, standard query parser is probably a good place to start. Now we are considering standard syntax, class standard syntax parser in package org.apache.lucene.queryparser.flexible.standard the parser for the standard Lucene syntax. Now we are considering query parser, class query parser in package org.apache.lucene.queryparser.classic. This class is generated by Java CC. The most important method is queryParser base.parse string. The syntax for query string is as follows. The query is series of clauses. Clause may be prefixed by plus or minus sign indicating that the clause is required or prohibited respectively, or term followed by a colon indicating the field to be searched. This enable one to construct queries which search multiple fields. Now we are considering class complex praise query parser. In package Apache Lucene.queryParser.complex praise query parser which permits the complex praise query syntax. For example, this one, the Jonathan title mark and Peter's asterisk here. Now we are considering extendable query parser. Class extendable query parser in package Apache Lucene.queryParser.ext. The extendable query parser enables arbitrary query parser extension based on the customizable field naming scheme. The Lucene syntax allows implicit and explicit field definition as query prefixed followed by a colon character. Extensible query parser allows to encode extension keys into the field symbol associated with the registered instance of parsed extension. A customizable separation character separates the extension key from the actual field symbol. The extensible query parser split the extension key from the field symbol and tries to resolve the associated parse extension. If the parser can't resolve the key, or the field token does not contain the separation character, extensible query parser yield the same behavior as it the superclass query parser. Otherwise, if the key is associated with the parse extension instance, the parser builds an instance of extension query to be processed by the parse extension.parse extension query. If the extension field does not contain the field part, the default field for the query will be used. Now we are considering class queryParser in package Lucene.queryParser.surround.parser. This class is generated by Java CC. The only method that client should need to call is parse method. Now we are considering class queryParser in package Apache Lucene.queryParser.xml. Assembles a query builder which uses only core Lucene query objects. Now we are considering overview in query parser syntax. In package Apache.Lucene.queryParser in .classic. Before choosing to use the provided query parser, please consider the following here. Although the Lucene provides the ability to create your own queries through its API, it also provides a rich query language through the query parser, a lexer which interprets the string into a Lucene query using Java CC. Generally, the query parser syntax may change from release to release. This page here we describe the syntax as of the current release. If you are using a different version of Lucene, please consult the copy of the docs or query parser syntax .html that was distributed within the version you are using. Before choosing to use provided query parser, please consider the following. If you are programmatically generating a query string and then passing it with the query parser, then you should seriously consider building your queries directly with your query API. In other words, query parser is designed for human entered text, not for program generated text. To the tokenized field are best. Untokenized fields are best added directly to queries and not through the query parser. If a field's values are generated programmatically by the application, then so should query clauses for this field. The analyzer which the query parser uses is designed to convert human entered text to return terms. Program generated values like dates, keywords, etc. should be consistently program generated. 3. In a query form, fields which are generated text should be used the query parser. All others such as date ranges, keywords, etc. are better added directly through the query API. A field with a limit set of values that can be specified with the pull down menu should not be added to the query string which is subsequently passed, but rather added as a term query clause. Now we are considering terms. A query is broken up into terms and operations. The class terms in package Apache.lucene.index access to the terms in a specific field. There are two types of terms: single terms and phrases. Multiple terms can be combined together with Boolean operators to form a more complex query. Note that the analyzer used to create the index will be used on terms and prices in the query string. So it is important to choose an analyzer that will not interfere with the terms used in the query string. Now we are considering fields. The Lucene supports field data. The class field in package Apache.lucene.index provide the term index for fields that have it and list which fields to. This is primarily an internal experimental avoidment by API, although it is used to expose the set of term vectors per document. Lucene supports fielded data. When performing a search, you can either specify a field or use the field default field. Field names and default fields is implementation specific. We are considering term modifiers. Lucene supports modifying query terms to provide a wide range of searching options. Wildcard searches, regular expression searches, fuzzy searches, proximity searches, range searches, boosting of term. Now we are considering Boolean operations. Boolean operations allow terms to be combined through a logic operations. Lucene support and, plus, or, not, and dash as Boolean operators. Not Boolean operators must be all caps. Now we are considering grouping. Lucene supports using parentheses to group clause to form subqueries. This can be very useful if you want to control the Boolean logic for a query. Now we are considering field grouping. Lucene supports using parentheses to group multiple clauses to a single field. Escaping special characters. Lucene supports escaping special characters that are part of the query syntax. The current list of special characters are plus, minus, ampersand, two or symbols, and blank sign, and or not sign, and open bracket, close bracket, open curly brace, close curly brace, open square bracket, close square bracket, caret and double quotation, title, asterisk, question mark, colon, backward slash, and forward slash. To escape this character, use the backward slash before the character. In exception example, we can consider pass exception, the class pass exception. This exception is thrown when pass errors are encountered. You can explicitly create objects of this exception type by calling the method generate pass exception in the generated parser. You can modify this class to customize your error reporting mechanisms. So long as you retain the public fields. This is in package org.apache.lucene.queryparser.classic. As an error example, we can consider this occurred in Confluence. Invalid syntax cannot pass, syntax error cannot pass, equal at the com.altasian.confluence.search.v2.lucene.mapper.abstract text field query mapper dot try parse, abstract text field query mapper dot java, coarse binary syntax cannot pass, syntax error cannot pass equal at org.apache.lucene.queryparser.flexible.standard.parser.standard syntax parser.generate parse exception standard syntax parser.java.